Welcome everyone. So this is our 99th live stream geometry, and we have 2 other people here so far, and more will probably join later. And I'm going to do some more problems from the geometry discussions and problems Discord server. So I always go there when there's no latest competition that comes out. But Ravi on the session currently just mentioned that there's another competition. So once that's over, then maybe I can go over those. So if you want to join us in the future, feel free to email me at mgreenvieta1@gmail.com. We meet every Sunday at 8 a.m. US Central Time. All right, so I am going to share my screen. So let's start off with, this looks like an easier problem. So let's see what we can do with it. Trying to maximize, 1 second. I wonder if there's a keyboard shortcut to maximize the screen, but sometimes I have trouble doing it. Let's see. There we go. Okay, so we have a triangle ABC, and then we draw the tangents at B and C. So it's kind of like a Semidian configuration. And they intersect at T. So we draw the tangents. 1 tangent, 2 tangent, and they meet at T. And then X and Y are any 2 points on AB and AC, so that TX and Y are collinear. So we are going to want to extend AC, and let's see if we can make this diagram a little nicer. We want maybe something like this. And then this would be Y. And this would be X. And we want to show that the orthocenter of OXY lies on BC. All right. Let me draw this in a little better. There we go. And here's triangle OXY. And let's draw the orthocenter of it. I'll call it H. There we go. All right. So is there another way we can define H? Let's see. I guess one thing we could do, was someone about to join for a second? It looked for a split second like it was saying someone wanted to join. I mean, we could try to break the symmetry by, we could take a perpendicular, there's Nguyen. All right, thanks for joining, Nguyen. So this is our first problem. So yeah, it's a fairly simple configuration. We have a triangle ABC. T is where the tangents at B and C intersect. Okay, H is the pole of XY. how do you know that? Oh, is it just because we know OH is perpendicular to X? OH is perpendicular to XY. That I get. And draw the intersections of XY with a circle. And you get a harmonic quad. So DBEC is harmonic. And so the tangents at, okay. So basically we could draw this point, and then we have to show that that point is actually the orthocenter. Is that obvious? Let's see. So DBEC is harmonic. And so OH is perpendicular to XY. And then we need to show the other two, right? So OH is perpendicular to XY, we know that. We need to show either that XH is perpendicular to OY or obviously this is the midpoint of DE. I wonder, like, one way maybe we could do it is we could draw this circle. I don't know if that really helps. Whoops, sorry. I need to do that. Although maybe that would be good to draw. All right. So we've made a lot of progress here. We know XY is the polar of H with respect to the circle. What else do we know? These triangles almost look, but they're not isosceles. I think it's just, yeah, it's an optical illusion. So, I mean, another way to say it is we want to show X is the orthocenter of OHY, right? And what we could do, basically that means the reflection of X over OH lies on this circle. And we know F is the midpoint of DE. So maybe that would help. Let's see. Okay, so sorry, let me check the chat again. YX DE is harmonic. So Y belongs, yx dE. That's harmonic because if you project onto the circle, then you get, yeah, the harmonic quad. So, okay. So that means y belongs to the polar of x. And y belongs to the polar of x. And h belongs to the polar of x. So yh is the polar of x. And so that solves it. Very interesting. I like it. Okay, so I'm going to write it up. Okay, so let xy intersect the circle at D and E. Then here's my understanding. So then DBEC is harmonic. So you could also say it using poles and polars, I guess. I guess another way to say it is x lies on what's another way to say this? I'll just do it like this. DBEC is harmonic, and so that means that we could call this H prime. So yeah, so like BC is the polar of x. Well, no, sorry. But yeah, DBC is harmonic, implies the tangents at D and E. Or at a point H prime. We call H the pole of xy. Yeah, okay. So if H is the pole of xy, so I'll just write it like this for a while, but and once we have this, we have yx dE is harmonic. So first of all, we have ABEC is harmonic. And then if we project BBEC, and if we project through A onto the circle, we have yx dE is harmonic. And so X lies on the polar of Y, or Y lies on the polar of X. So H prime also lies on the polar of X. And that means that YH prime is the polar of X. And that means that OX is perpendicular to YH. Or YH prime. And that means that H equals H prime, which means that the orthocenter H of OXY lies on BC. All right, so I'm going to move on to the next one. Let me think about this a little bit more. So yeah, like I don't think I needed this like harmonic. There are probably ways where I didn't need to say like this is a harmonic quadrilateral. I could just use poles and polars, right? So let me think about what my wrote for just a second. If H is the pole of XY, then it belongs to BC. Okay, so I think here's what it is. So we know BC is the polar of T. Yeah, I think this is good enough. All right, I'm going to move on to the next problem. So here's a harder one. So I'm curious what you guys think about this one. It's a short statement, but it uses this immediate point. So a conjugate is kind of more like I think it's more that they're inverse. So I mean, conjugate, there's like isogonal conjugates, there's harmonic conjugates. So like saying X lies on the polar Y, I think the only way to say it is just that X lies on the polar Y, or Y lies on the polar X. When you conjugates are usually, because the problem with saying that they're conjugate is that there's usually only one point that's the conjugate. So like, but there's infinitely many points that lie on the polar of X and Y. So that's why I wouldn't use that word, but yeah, I guess people would probably understand what you meant. Yeah. So sorry, I'm gonna go back one more time. So ED, yeah, you could say like EDX and Y are in harmonic conjugation. But I think it would be important that you like mention the E and B also if you were to say that. Okay. So here we have O as the center and H is the orthocenter. There we go. And then we see where does BH meet OC and where does CH meet OB. This feels a little bit familiar. So I feel like I've seen something like this before. So we have X and Y. And L, sorry, this should be X. I'm going to draw the feet of the altitudes because I think it'll help. So yeah, I should actually draw this whole ray. All right. And yeah, maybe we'll eventually want to see where it meets the circle, but for now, I'll just draw this. And we draw the median point. So I'm going to do that. I don't know what, so I don't know which triangle center that is in GeoGebra. So I'm just going to draw it manually. Oh, it's triangle center 6. Okay. I'll still draw it this way just because might be helpful. But yeah, obviously I want to make it easier to see. So maybe something like this. Yeah. Yeah, I want to see that bottom point more easily, but the way I drew it, it'll disappear if I move it too far away. Yeah, so let's see. I think that's okay. All right, so L, where's L? That would be L. And we want to show that OL bisects XY. I think this figure is too messy. I'm gonna redraw some stuff here. Let me draw this from scratch. So actually, yeah, I'm just not going to draw the tangents. Okay. That's L. And okay. This is OL. So AL is a symmedian, BL and CL are also symmedians. I don't know if it'll help to like extend CO to meet the circle or extend BO. OL is the radical axis of the 3 Apollonian circles. So what are those? What are the Apollonian circles? Is that like BEBC or something? So I'm going to draw the other for the altitude. Oh, if the A internal angle bisect or an external. Oh, okay. All right. So let's draw that. Might make the diagram a little tricky, but let's first just draw something and then see how it looks. Okay. Wonder if there's a simpler way to draw it. Let's just draw two of them for actually it probably would have been easier to draw them from B and C, right? So I'm going to do that. I'm going to draw it from B and C instead because it's more symmetric. Okay, so we need to calculate the power of the midpoint of XY with respect to those circles. Okay. So yeah, maybe we could just draw the B one, and then like the same argument would follow from the C one. Okay, so we want to see where this intersects that. How should it's the best way to draw this? It's going to be a tricky figure. Yeah, the diagram does not want this. All right, let's try that. So this, and this. And if we take the midpoint of XY, we want to show. So I guess, yeah, we could hide L if we try this approach. We want to show the midpoint of XY. We want to calculate the power of it with respect to that circle. Yes. So yeah, I didn't know about that theorem. That's interesting. Do you remember the proof? The proof that OL is the radical axis? So first, let me think about why O would lie on that. So the power of O, is OB tangent to the circle? It must be an angle Chase shows that. Okay, so the power of O with respect to all three circles is just the radius squared, so O lies on it. And then the median point, I wonder if that's something similar. Sorry. The power of that with respect to that circle. Okay. And BK is the B median. Okay. So BL times LK is the power of K. That must just be an angle chase to show that that's the median, right? And then BL times LK is AL, yeah. Interesting. It's really cool. All right, so we want to show that we want to find the power of J with respect to those circles, where J is the midpoint of XY. One sec, I'll be right back. All right, thanks for waiting. So let's think about this. So like angle CBK is CBY plus YBK, and we said that this YBK is tangent. So YBK, oh, and BO and I think I see YBK as a median. Yeah, I think it's just an angle chase. Once you know that. Okay. So the midpoint of XY. Yeah, like every point on it satisfies that ratio. It's a set of all points where It's this, like every point on it, the angle bisector meets the side of the same point. Yeah. Let's try drawing the tangents from J. I wonder, is JG tangent to it? I don't. It almost. No, it's not. So power of x would be bx times xd. Sorry, bx times bd. Is that so if I reflect b over ac? Oh yeah, because this is a oh. Wait, it's wrong? Are you sure? Because isn't this a diameter of that circle? Oops. Why is it wrong? Okay, so yeah, it's right. So we want to show that bx times bd is cy times ce. And that feels like it has to be easy, but you guys are going to beat me to it probably. So let's see. So BD times HD does the reflection of C with respect to AB lie on it? Are you sure? Oh, the other Apollonian circle. So yeah, we'd have to draw the other one in, but it should. Wait, so that's the power of x. Oh, but we need j, not just x. That's the power of x with respect to this circle. And then we can find the power of y with respect to the other one. Then j is the midpoint. Let me try some. So yeah, how do we use midpoints? Like when it comes to powers, I feel like there might be a way to do that. Just not sure. So the center of the circle is the midpoint of IG. J is the midpoint of XY. Yeah, how do we use that J as the midpoint of XY? Maybe we could use the Gauss line. So we have this quadrilateral right here. We have J, N, and then how would that work? Are J, N, and some other point like collinear? Well, I don't know how much that really matters. J and N are collinear with a 9-point center. That's interesting. Could be useful. By the Gauss line. Okay. Whoops, X is the wrong point to use there. And it looks like it also goes through that point. Yeah, because that's collinear with a 9-point center. Okay. I'm going to hide it for now just because I don't know if it's that useful. Hey, Akan, thanks for joining. So we're on the second problem. And they knew a lemma that looks pretty useful. So yeah, Ravi told me an interesting lemma on this. Looks like he's connecting to audio. But basically, if L is the Samidian point, then OL is the radical axis of the 3 Apollonius circles. So I didn't know that. That's an interesting lemma. Yeah, so let's see. How can we calculate the power of J with respect to this circle? I guess one thing we could try to do, we could try to use Casey's theorem. Yeah, I get there's Casey's theorem is the main one that I think of. Casey's theorem, it says if you have a point and 2 circles, Any point in any two circles. Let's call them circle alpha and beta. Or let's calling it D1 and E1. Let's call it X. Oops. Why can't I say X? Circle A. And let's call this circle, I don't know, M. So Casey's theorem, I use this a lot. It says the power of n with respect to k minus the power of n with respect to m is equal to, actually, let me draw the centers of these circles. It's 2uv times the distance from k to rs. K to the radical axis of the two circles. So this is, it's also called like linearity of power of a point. There's a couple different names for this, but whatever these two circles are, and wherever n is, this is always true. So yeah, n can be anywhere. It can even be on one of the circles, which is pretty useful. The distance from the perpendicular distance from n to rs. So yeah, you have to drop a perpendicular. Yeah, I've used it in a couple videos before on my channel. It's not bad. So NW basically. So yeah, if n is on the circle itself, then it's basically just, or let's say n is on this circle, then it gives you a way to find the power of n with respect to this circle. Because this would just be 0. So yeah, it's a cool way of doing it. Yeah. So I'll just leave it there for now if you want, but yeah, if you look at my video on IMO shortlist, IMO 2019 number 6, you can calculate the power of J simply by Pythagoras. Oh, so Jm squared minus OL are equal. So the distance, that would prove it. Oh, if we could show the distance of x and y to OL. Let's see. So I'm going to check that, but I think what you're saying makes sense. So we're saying the distance YZ and the distance XA1 are the same. Yes. Yeah. So my is saying we can calculate the power of J by Pythagoras. So I'm guessing you mean like Jm squared minus mg squared. So, sorry, I think I've seen this before, but how would that prove it? I'm losing my my memory of these things. If and only if the midpoint light on that line. So OL is the radical axis of the B. Oh. I think I see what you're saying. So are you saying X and Y have the same powers with respect to the Apollonius circles? So are you saying like bx times bd equals by times equals cy times ce? That doesn't look true. Okay. Power of j with respect to this circle is ij squared minus ib squared. Wait, ij or m? Wait, I'm confused. Power of j with respect to this circle? Oh, the power of m, the power of j with respect. Okay, so mj squared minus mb squared, which is mb squared. Okay, now you're using the replace all I by m. So then you're using a formula for the median, and then ix squared plus iy squared, or sorry, mx squared plus my squared equals md squared plus xd squared. So ix squared is okay, I see that. Mx squared plus mb squared. And then that last expression, md squared. So the last expression is symmetric, so that basically proves it, right? Is that right? Minus cd squared, or is it? Okay, let me write this out for a sec. So I copy it. And okay, yeah, so I'm going to type it up. J. Just write it like this for the people on the channel. I'm going to delete Casey's theorem for now, but yeah, that's interesting what Robbie was saying. So But let's see if we can do it this way. I'll add some LaTeX in just a second. So it looks better. How do I make it go to a new line? It didn't work. Let's try this. That kind of works, but all right. So the power of j with respect to that circle, it's mj squared minus mb squared. And mj squared, we're using the fact that mj is a median. So it's 2mx squared plus 2my squared minus xy squared over 4 minus mb squared. That's the formula for the median. And then mx squared plus my squared is mb squared plus xd squared. Then the other is but the thing is, I don't know about this mb squared plus by squared. So is this, oh, this is a right angle. Okay. And then md squared xd squared is xc squared minus cd squared. Okay. So an MB is obviously like the radius of the circle, so XY so MB, let's see. The MB squared will be eliminated. Okay, so this part, okay. I'm gonna type out, just write out what you just put. So yeah, if you substitute this in, then you're saying the MB squared goes away. Because you'd have two. Yeah, I was gonna say, so. But I still don't, so you're saying MB squared is eliminated. But if we plug this in, we would have 2MB squared over 4, which is MB squared over 2, right? And then minus an MB squared. So it doesn't, does it go away, or is there still like a minus MB squared over 2? Yeah. Yeah, no, this does look good. Yeah, this is definitely a step in the right direction. So but like does M doesn't go away, right? There's still, yeah, like we could try to see what it looks like when we set the two equal. So yeah, we can kind of ignore the x, y, because that's on both sides, right? MB squared minus MB squared equals CD squared minus CB squared. So that would be useful. Yeah, I see what you're saying. So if we substitute that, then the MB squared would go away. Okay. So let me write this out on paper. I wonder if this helps it. Yeah. I like this. This is looking good. So that would be 2MB squared minus BC squared. So once we substitute that in, 2MB squared minus BC squared plus XC squared plus BY squared. We'd have that, and then we'd have twice it. So we'd have 4MB squared minus 2BC squared plus 2XC squared plus BY squared. That over 4, and then minus MB squared. Okay, so we need to show that BY squared minus BC squared over 2 is equal to CX squared. Yeah, BC can be ignored. Yeah, you're right. So BC and XY can both be ignored. Wait, I think I'm missing something because now I'm just getting that BY squared equals CX squared, or that we have to prove that. And I don't think, yeah, BY does not equal CX. So something is going on. Oh, I think I might see what's going on. Yeah, it feels like it should work. So mx squared plus my squared equals xc squared plus yb squared plus CB squared minus 2MB squared plus 2MB squared. And then if you double that and you plug it in here, so do we just want to show that MB? I think maybe it reduces. So let's say we draw the center of the other Apollonius circle. Are the diameters of the two Apollonius circles the same? Is that true? I think it might reduce to that. Do all three Apollonius circles have the same diameter? I feel like that would be like I feel like I would know that, but then again, there's a lot of easy things I don't know, so. No, okay. So then I'm just missing something here. Yeah, okay. So let's write this out. So basically, if we use this fact, then so yeah, let me just write everything out. So if we use this fact, then that means so if we write, so MB squared is MB squared plus CB squared minus CB squared. So if we plug it into this, that means MX squared plus MY squared, looks like Robbie's coming back on, is equal to, substitute it. So we've got 2MB squared. The CD squared would cancel. We get plus XC squared minus CB squared plus BY squared. So we have that. And then that implies that the power of J with respect to M, if we take that and we plug it in here, we get twice that, but then we're dividing by 4. So MB squared cancels. We would get basically half of XC squared plus BY squared minus CB squared, and then minus XY squared. I think this is right. Tell me if there's anything wrong here. Okay, so I'm taking this and plugging it in here. Okay, so we need to draw the C1 also for the B circle. So CB we can ignore, XY we can ignore. We need to see that XC squared. No, aren't we fine here? Because this is symmetric with respect to everything. I think this solves it. If this is true, everything here is symmetric. Right? Yeah. Okay, so this solves it. So yeah, we're good. So I'm just gonna write up the full thing. That's cool. I'm glad we solved this. So by a well-known lemma, OL is the radical axis of the 3 Apollonius circles. Now I'm going to write what that is, i.e. the circles through a vertex and the foot of and the feet of the internal and external bisectors. Angle bisectors. Okay, so that really was the key lemma to this problem. Without that, the whole thing, yeah, it just doesn't go anywhere. So once we have that, I could just say label the points as shown, because I'm too lazy here. So this is symmetric with respect to B and C. Respect to B and C. So we have the power of J with respect to M is equal to the power of J with respect to N. So that means that J lies on the radical axis of Apollonius circles. Apollonius circles. And that means that OL bisects XY. All right. So let's move on to the next one. This is a fantastic proof. And yeah, who knows if there's a way to get around the algebra, but I don't care. I like it. All right. This one looks kind of interesting. We have a triangle ABC, and we have 3 altitudes that concur at H. And then we have the midpoint of BC and EF. So yeah, it doesn't sound like it's that complicated. Oh, is that the other solution to the problem we just did? Oh, they use Casey's theorem. Nice. So there is a way to do it using that. So M is the midpoint of BC. And N is the midpoint of EF. And we draw the line from M parallel to EF. So MN is perpendicular to EF because M is the center of the circle BFEC. To draw that parallel line, EF is parallel to the tangent at A, I believe. And DE intersects that line at Q. And DF intersects it at P. Okay, interesting. Let's see if we can make that a little bigger of a triangle. So we have P and Q. That's P. And this is Q. And BP intersects CQ at R. And we want to show the circumcenter of RMN lies on AB, which is the altitude. So this is kind of a very random configuration, but interesting. I have to hide and redraw a lot of stuff because there's just too much. Whoops. Hide this. Hide this. hide this, hide this, hide this. And now I go in and redraw everything. Okay. DE, DF, and BP intersects CQ at R, and M is the midpoint. So we have RMN. We could draw the circumcircle of that, but it's saying that the circumcenter bit lies on AD. That's what we have to prove. I mean to do that. So I wonder if AD passes through this point. I don't think it does. No. It's interesting. So G is the circumcenter. Maybe there's something special about G. One sec, I'll be right back. Okay. I'm back. Let's see what time it is. It's not even 10:30 yet. All right. So M and N are easy points to understand, but R is a little bit trickier. I forgot to draw something. So DF intersects. Oh, I forgot to draw that parallel line. That's right. So this is parallel to EF. So it's also perpendicular to MN. In fact, this is a cyclic quad, I think. Oh, no, it's not, because, oh no, this is a right angle and this is a right angle. This is a trapezoid right here. It almost looks like a rectangle, so see if I can make it more trapezoid looking. Yeah, I guess if I make A higher, it looks a little more like a trapezoid. But I think that looks okay. So we see, where do DE and DF meet this parallel line? Obviously DPQ and DEF are similar, homothetic. So once you have P and Q, then you get R. So I wonder, what if we let BQ intersect CP? I'm just curious. I wonder if that also lies on the circle by symmetry. Yeah. So yeah, something is going on here where there's some kind of symmetry. I haven't proved it, but looks like that's the case. If that's true, maybe we could use even Ricard's theorem, like let MR intersect BQ at a point. Well, if you look at IR, I don't think that's parallel to BC, is it? Maybe it is. I don't think it is, but oh, it is parallel to BC. Because M is the midpoint. That's a good point. Interesting. So if we do like a degenerate form of Ricard's theorem, oh well, I'm just curious. Is MRIN a trapezoid? I don't think so, but I'll check. Huh. I don't think MB is actually parallel to MR. I think that was, yeah, that was a coincidence. Yeah, I'm gonna erase those. Well, that one I'm gonna leave, but NR. So basically, first we're saying AB bisects. Well, not bisects. I think so. I think we're saying AD bisects IR, right? And we don't even really know that I is on the circle yet, but like this would be the midpoint of IR. And I wonder if I don't think this point is the midpoint of the arc. I would be very surprised if that were the case. Let's see. Yeah, it's not true. It's like GEO King got disconnected. Could it be that I don't think Rn passes through A, but I'll check it. Wait, that seems. Is that really true? Rn and A are collinear? That is true. Huh. I do not know why that's true, but that looks true. Okay. So somehow we can prove that Rn and A are collinear. Which is the same as saying, so AN is the median, right? Unless I'm crazy, AN is a median, right? Yeah. So we want to figure out how to use that fact. Sorry. In fact, I wonder if ABCR is cyclic. No, because then it would be harmonic if that were the case. I mean, one way to show something lies on the median is to drop perpendiculars to each side. So maybe we can do that. Like if we drop a perpendicular from R to AB, how could we use that? Oh, I guess Marco just had to leave. So yeah, we want to show R lies on the median. We know DEF and BPQ are homothetic. So yeah, showing it lies on the median. Let's see. Oh, well, I don't think these meet on the circle. I would be surprised if that were the case. But can we say anything about this distance right here? This perpendicular distance. Do we have any similar triangles? Does this equal? I wonder if this angle is equal to something else. That's 61.3. It's not that. Curious about this point K. Okay, I don't think there's anything special about K. I thought there might. I doubt those are current. Yeah. This one looks hard. So we just haven't used a lot of stuff yet. Like I think we need to do some projections. So like the way R is defined is a little tricky. You want to go back to this later, or you want to keep trying it? You can try it for a little longer. Okay. All right. Let's try. This one looked kind of interesting, but I'm going to. This one looks a little easier. Let's try one that's a little easy just for a second. So we have a triangle ABC, circumcenter O, and